Okay, both these warm-up problems lead into what we're going to be talking about today. I've got a two-way table here. Jason, anytime I see a two-way table, what's the first thing I do before I answer any questions or anything like that? I
draw a Venn diagram.
No. Nolan, first thing.
Do you total up the
columns? Let's total them up. Okay, I got a two-way table here. Let's get all these guys totaled up. Now this was nice of me. This should have been 100. So each one of these is just the decimal of what it would be. It would be a little bit tougher if I'd have had 200 over here. Finding the individual values for the Venn diagram would have been a little bit tougher. But let's go ahead and do this. Looks like we've got 50 males, 50 females. We've got 40 people that said yes, and 60 people that said no. Okay, so just looking at this, you know, the probability that think women should be in combat is 40%, looking overall at it. Okay. All right, now let's create the Venn diagram for this particular problem. Now remember, a two-way table and a Venn diagram are the same exact thing. It's just a slightly different form for it. Okay, so don't think these are all that different. They're not. I do want these in percentages though, or proportions. So James, help me out here. Which ones you fill in first?
I did male without, that said no. Or the middle.
Did the middle? Okay, and what you have there?
0.32.
Yeah, that's right there. It should have 0.32. I asked you to make the decimals for when you're doing a Venn diagram. Yeah, that one we know. Okay, 32% both were males and answered yes to this particular problem. How about males only?
0.182.
Yeah, that's right here in our two-way table. Yes only?
0.08.
0.08, and then what was the percentage that were outside of male and yes?
0.42.
0.42. So we've got our Venn diagram. Okay, the next question I ask is, are the events being male and answering yes to this question that women should be in combat, are they independent or not? Now let's just think about this logically for a second. The probability that someone's going to say yes is 40%. Now remember what independent means. If I know that person's a woman that I'm asking, do you think that might change the probability of them thinking women should be in contact? You think that might change it off of the 40%? I don't know, maybe. Or if I know that person's a man, I know that. Does that change the probability that they think women should be in combat? Okay, so that's the question that's in your mind. Logically, I'd say, you know, it might. You know, genders might have a relationship, might have different feelings about whether women should be in contact or not. Now, in this particular problem, we can actually prove that mathematically. So how do I go about doing this? Proving it mathematically. James.
Well, you add, no?
Well, what am I going to use? What?
Might use that rule.
Rule 7? I'm going to use the general addition rule to prove whether things are independent or not?
No, then I'd use 6.
Yeah, I agree. Okay? We learned, this is critical for what we're going to talk about today, we learned that if two events are independent, then I can simply multiply the individual probabilities together to figure out the probability of them having that in common or having that intersection. So let's go backwards on that. This formula, if this formula works, then we know those two events must be independent. So the first thing you should have written down is the formula that we're going to use. Now, get away from A's and B's. I know that's how it is on your formula sheets, but I want you to start writing down what these abbreviations are using better letters to do it. So here I've got M and Y for you. So how are we going to use this formula right here? How would I write the formula?
P parentheses.
The probability of?
M and Y equals probability of M times probability of Y.
Correct. And we're wondering, is that true? That's the question that we have. If that's true, if that formula works, then, you know, gender is independent of how they would answer that question about women in combat. All right, from our Venn diagram, we know this is 32%. Now, what is the probability of men here? We can get this off of our table. And what was the probability of men in this particular study? That's 50%. And what was the probability of yes? Okay, 40 out of the 100 said yes. So this is 32%, and this is, what, 20%? They are not equal to each other, so therefore we now know for a fact that there is a dependence between how someone would answer that question, okay, and their gender. Okay. So when we went through kind of the logic of it, it squared away with what we ended up getting. All right, number two. Number two can be solved quite easily with the Venn diagram, but I want you to start getting better, okay, at reading these words and changing them to symbols. Okay, that's something you're going to have to do tonight. You're going to have to be able to read a sentence and then change it into symbols and then figure out which formula fits and which one we're going to use. All right, Jenna, help me out here. Change. A company feels the chances of winning the first job is 60%. How can I change that to symbols? Yeah. That's just fine. Earlier today they said the probability and they put J and then sub 1, meaning the first job is 60%. That's a good way to go. Okay, get away from A's and B's, and so that when you read what you have after this, it kind of makes sense in the problem that you're doing. Okay, for the second job? Okay, and is there anything else that's given to you here?
Probability of MC 1 and 2
Yes.
is 0.2.
Okay, this is a skill you're going to have for tonight. Okay, take a look at what was given to you, and then write up abbreviations, okay, of what that means. And now, what are we looking for? So what are they asking us for in this problem?
The probability that you'll have 1 or 2.
Yeah, and be careful there. I kind of said it in a weird way. I said what's probably getting one job or the other or both. I could have just said what's probably getting one job or the other. Okay, I could have even said at least one job for this. Okay, they all mean the same thing, and it's our union. So, what formula are we now going to use for this? Okay.
Probability of 1.
Good.
Probability of 2.
Good.
Minus the probability of 1 and 2.
Very good. And unfortunately, I've got 4 unknowns here, but they gave us 3. Okay, so we can just go straight to our formula. So this is going to be 0.6 plus 0.4 minus 0.2, which ends up with 80%. So in the long run, chances of the probability of getting at least one job or one job or more or one job or both is 80%. Okay? Skill you need to have for tonight. All right. I have a new symbol for you. It's called a conditional probability. It's not divided by. It looks like divided by. It looks like the divided by symbol, but it's not the divided by symbol. Okay? It's a conditional probability formula. So let's go over here to number 3 and 4 of our warm-up. The first one says, given someone is female. Okay, we did this way back when we did conditional formulas. Given someone is female, find the probability that they said yes. Okay, how do I do this, Haley? How do I figure out, just from this chart, given that they're female, the probability that they said yes?
Take the number of guesses and divide it by the total.
So, number 40 over 100? Is that what you're saying?
8 over 40. Number of guesses for female.
8 over 40? So,
8 over 50.
8 over 50. So why are you choosing those?
The probability for number 3, right?
Yeah, we're doing number 3.
Well, it says given someone's female.
So how many females do we have? 50. That's it. Given that they're female, that's already happened. I know I'm talking to someone who's female. All I care about is this row. This is the whole world. This has already happened. So I only care about those 50 people. Now, of those 50, how many said yes? Is that the right one? We did the right one. 8 over 50, which turns out to be 16%. Okay? All right, I have another way to write this now. Okay? And this is how we're going to write the symbols for what this is. This is the probability that A happens given B has already happened. Okay? So, for this particular problem, we would say that this is the probability of saying yes given they are female. Okay, so this means it's already occurred, and this is the probability, once this has already occurred, that they're going to say yes. And notice this, take a look at this. If I know someone's female, the probability of them saying they want to go to combat is only 60%. That is different than what it was overall. So if I know someone's female, they're less likely to want to go to combat based on that particular chart. Dependence. Knowing someone's female changes the probability they're going to say yes. Okay, conditional probability, how do we use that? All right, it leads us into what we're going to talk about today, and this is the general multiplication rule. Let's take a look at what this looks like on a tree diagram. Here I've got our old problem. I'm going to deal you 2 cards. Now this time when I deal you after the first card, I'm not going to put it back in the deck. Okay, so the deck is going to change. Once you get a card, the deck is going to change. Okay, so this is what it'll look like. So the probability that you get a heart, there's 13 hearts in the deck, 52 total cards, so this is 1/4. Probability that you don't get a heart is 3/4. Okay, so that's the probability of getting a heart. Now where conditional probability is right here. Once I've already got a heart, see this is where I'm at on the chart. This has already happened. Once I've already got a heart, what are the chances I'm going to get a heart on the second one? Well, now there's one less heart in the deck. There's only 12 hearts in the deck over the 51 total cards. So that's how I would write this. Given I already got a heart, the probability that the second one is going to be a heart is 12 over 51. So one of the key things I need you to notice here is this is just one event happening. This is already transpired. Over here, I already knew I had a female. Already done. Now tell me the probability of getting yes. So when you write something like this, you're going to see, oh, there's 2 events here. There must be 2 things that are going to happen. No. You're only trying to figure out the probability that one happened because this already happened. Okay, so be careful here. This is just the probability of one event happening. You're going to confuse it with the probability of 2 events happening. Now remember we learned we could just multiply our way down the tree. We've done this before when they were independent. Now they're dependent. So if I'm trying to figure out the probability of 2 events happening, I start right at the beginning, and there are 2 things that are going to have to occur. It should kind of make sense to you. What's the probability of getting 2 hearts? It's the probability of getting 1 heart times the probability that you'll get another heart given you got one on the first card. So if I wrote that out, it would be the probability of getting the first heart, which is 13 over 52. Times the probability of getting the second heart given I got one on the first. Just multiply our way down the tree.
On your chart, isn't it 38 out of 51 on the H1 happening?
Okay, so this guy, which one, this one?
No, the other one, yeah.
Okay, so I got a heart on the first one. Now what I'm asking for here is what's the chances the second card is not a heart? Okay, so aren't there 13 and 39 to start? Does everybody catch the subtlety here? If I ask the question, hey, what's the probability that I don't get a heart given I got one the first time? I start right here. Now I know I got 51 cards left, but aren't there 39 of them that are not hearts? Again, if I'm just finding this, there's no multiplying to do. I'm not multiplying my way down a tree. I'm just finding the probability of one event given this has already happened. Okay? So that hopefully will illustrate this formula. It should make a little bit more sense to you. If I'm trying to figure out the probability that 2 events happen, it's the probability that one of them happened times the probability the next one's going to happen given the first one already occurred. And that's the general multiplication rule. We call it the general multiplication rule because it works whether it's an independent event or a dependent event. That's the general formula that works. Remember we did this when we were putting the cards back in? So it was a 1/4 chance here, but then a 1/4 chance again because I put the card back in the deck. And you just multiplied your way down. So whether they're independent or dependent, this formula is going to work for you. All right. Now, this is in your green sheets. However, it's not in this form. Go to your green sheets and find it. It's right below the general addition rule. They wrote it this way, but I need you to know they're the same exact formula. What would happen here if I multiplied both sides by the probability of B? These would cancel. Probability of A given B is the same as both things happening divided by the probability that B has already occurred. Now this, some of you are like looking at this like, I don't understand how this works. You just did it right here, didn't you? Go back to this. Didn't I ask you the probability that you would get a yes given a female? And didn't we have 50 females? Didn't you put the females down here? That's how many we had in the world? 50%? I could have made that a decimal, 50%. So what's here is my world. That's on the bottom. That's what I'm considering this whole thing out of. Now the top was the chances that they said yes and female. That's why that went on top. That's the same thing we've got here. So your challenge tonight, you're going to be given a question, okay, like number 2 in the warm-up. You need to change what you have to symbols somehow, and then figure if this particular formula works for you. You can write it like this, and let's say they give you this one and this one. Okay, you can solve for this. Or if you remember this particular formula, you can write this out as well. Okay, and then plug in the ones that you need. But like I said, you can just always write this one down and plug in the ones that you got. Okay, general multiplication rule. Trying to find the intersection of two events. Chances one of them happens, sometimes probably the other one happens, given the first one already occurred. All right. I thought this might be appropriate for AP Stats. Chapter 6 is brutal. Some of you are going to be going bye-bye. Okay, those of you just kind of been skating, this is when you go away. Chapter 6, 7, 8, toughest ones we got. That's why I brought this grade distribution chart out. This is probably what's going to happen in here. All right, I got a probability model here. Grades in AP Statistics. Got to get some chuckles. Does anybody understand what this thing even means? All right, let's go through this now. From this chart, what's the probability that a student's going to get a C? Yeah, 10%. We got that right there. All right, from the chart, what's the probability someone's going to get a D? How would we solve this guy?
It's the probability, so 1 minus...
Yeah, where'd you get the 1 from?
It adds up to 100%.
Yeah, aren't these all the possibilities? Okay, so we know if I've got the whole sample space over here, these probabilities have to add to 1. Go on.
And you subtract all 0.02, 0.05, 0.1.
From 1, see what's left. You could add these up, subtract it from 1.
Yeah.
What'd that come out to? Am I doing it? 0.4 what? So this is 0.43, 43% chance of a D. All right, the next one here, and I didn't write this that well. I want to know the probability that you're going to get anywhere from a C through an F. I could have wrote this, the probability of a C or a D or an F. There's another way I could have written it. Okay. What is the probability a student's going to get a C or a D or an F? How'd you get that? So you could just blindly add those numbers up? Isn't there some sort of a deal here we got to be worried about?
Yeah.
I got to worry about it?
Huh? No.
No? Why not?
Because
Now say it right. Last period they said it wrong. Why can I just add these individual probabilities up? Because these events are... Yes! Mutually exclusive. He didn't say the I word here. And what does mutually exclusive mean?
It means that they can't happen at the same time.
Very good. Can I give you a D and an F at the same time? I would like to, but can I? No. So I can just add these up individually. I like that very much. So what is the probability of getting a C or a D or an F? 0.93. Okay. So now I want us to answer this conditional probability. What is the probability given I've got a student, I know they got a C, D, or F, what is the probability that that student got a C? Go right to the formula. So rewrite it with your formula. Write the formula first. Don't start answering or multiplying or do anything. Just write the formula first, right here, and then we'll start plugging in numbers. You can write the formula as it appears on your green sheets here. I mean, that's going to be your form. All right, so what am I writing here? This is the probability of, let's go right from your formula. This is the probability of getting a C and a C through F, all divided by the probability of C through F. Remember, that's the denominator. That was the 50. We only care about the C through F students. Okay, all I did was take our general multiplication rule as it appears in our formula sheets. Now, I know I'm using different letters, but I need you to do that. Use the letters that equate to what the problem was about. All right. This is the first got you. What goes on top? I've got the probability, the intersection of the probability of C and the probability of C through F. So I can just do this, 10% times 0.93. Do that. In case you're saying no, why can I not just blindly multiply those two together?
Because you get a C or C through F.
Aren't I trying to find the intersection? Right? Of the two events? So, don't I just multiply the probabilities together to find the intersection? Isn't that one of our formulas?
If they're independent.
Good. If they're independent. Do we know for sure that the grade you get is independent? No, you don't know that yet. Have we done any math yet or done any work to see if the events are independent or not? In fact, these are not. Please don't do this. This is a very common mistake. You see that in the formula and you just blindly multiply stuff together. No! Now let's think about this logically now. What percent is the intersection? What do they have in common between students getting a C and students getting a C through F? It's what? It's just the C, isn't it? Isn't that what they have in common? The C is this 10%. The other group is the 10%, 43%, and 40%. Which what do they have in common? What's their overlap? Just that 10%, right? So the numerator here is 10%, and then what's the denominator? Yeah, we found that up here. Go figure out that. And you've got, in the long run, the percentage, if you have students that got C through F, whatever that comes out to is the probability that that student got a C. Okay? All right, last really big formula that we've got for this chapter. It's called the general multiplication rule. If I'm trying to find the intersection between two events, just multiply our way down. In case we got it in a tree form, that's really nice. But what they're going to do to you quite often is they're going to give you a question like this, change it to symbols, okay, and then plug it into the formula. Now, the most confusing thing that you're going to have when you're changing the words to symbols is you're going to get confused with that and with that. What is it? You're going to read a sentence, or they say, and you're going to ask yourself, is that a conditional probability they're saying there, or is at the intersection of two events. Here's your kind of only hint. This one is the probability of one event happening. This one is the probability of two events. So before I start, what are the chances two things are going to happen? So in this one, something's already occurred. You already know this to be true. In this one, you don't know anything to be true. You're just trying to find the probability that both of them occur. Okay? Questions?